Hello students, welcome back to my chemistry classes with you. And today it's the grand finale of the chapter solid state, right? So you remember, right, that I have taught you so much detailed thing about the chapter solid state. We have done all the theory part. After that, we moved on to the CBSE pattern questions, JEE main pattern question, and finally we are here with the JEE advanced pattern questions as well, right? So here also I have done the same thing. I have collected a kind of like 10 to 12 questions for you, and in those 10 questions I have taken them maybe from past year JEE advanced paper, or these are like kind of probable questions that can be asked in the upcoming exams. Now let us, without wasting any further time, let us directly move on to the very first question in the JEE advanced pattern exercise. And here on the screen you can see your question number 1. So question number 1 says that the correct statements regarding the defects in solids are. Like you need to simply say these are the 4 statements given to you. It's a multi-correct question. Maybe only one answer is correct or maybe more than one answers are correct, right? So you need to figure out that which of the following options are correct. Let us see what's the question. It says that Frenkel defect is usually favored by a very small difference in the sizes of cations and anions. To do this question, I think we need to take into account, okay, let us read the options. Frenkel defect is a dislocation defect. Trapping of an electron in the lattice leads to the formation of F center. And finally, Schottky defects have no effects on the physical properties of solids. So these are some mixed statements which are given to us, and we need to figure out whether they are correct or wrong. Okay, that means for 1, 2 and 3 options we need to consider something about Schottky defect. Also we need to take into account something related to Frenkel defect. Do you remember that I have taught you in my previous videos that Schottky defect was basically, so both Frenkel and Schottky defect were the examples of stoichiometric defects. So they were an example of stoichiometric defects. In the case of Schottky defects, what happens is, we simply say that the anions are missing from their lattice site. They are missing from their main lattice site. Okay, fine enough. But then the anion are missing, so cations will be more in amount. So in order to maintain electrical neutrality in the system, we say that the cations also will be missing from their lattice site. So they will also be missing from their lattice site, or you can say that they will be forced to leave their lattice site. Why is it so? This is because the size of the cations and anions are approximately same. That means there is a very small difference in the size of cations and anions. That is why the cations are now left with no other option but to leave the lattice site, right? However, when I will be talking about Frenkel defect, so whenever I am talking about Frenkel defect, we simply say that the anions will be missing from their lattice site. So the anions will be again missing from lattice site. But when the anions will be missing from the lattice site, what will happen to the cations? We will say that now actually what happens is the size of the cations and anions are way different from each other. So the cations are very, very small in size compared to the large size of anions. So rather than the cation being forced to leave the crystal, it is not asked to leave the crystal, it will go and occupy the interstitial voids. That means the cation is now undergoing a dislocation. This is undergoing a dislocation. Dislocation means that there is a change in the location. So there is a change in the location. Okay, in the case of Frenkel defect. Now let me come back and read the statements again. The first statement was Frenkel defect is usually favored by a small difference in the size of cations and anions. No. So whenever there is a very small difference in the case of in the size of cations and anions, then not the Frenkel but the Schottky defect is favored, right? So option number 1 is wrong. Fine enough. Moving on to option number 2. Option number 2 simply says that Frenkel defect is a dislocation defect, which just 2 minutes back I told you is a correct option. Fine. Moving on to the third statement, let us leave the third statement for time being because it is something related to F center. Let us leave it for 2 minutes. Let us directly move on to the fourth statement. Schottky defect have no effect on the physical properties of solids. See guys, I am saying, let us say earlier, we had cations and anions present in the system. So let us say the cations I am drawing in white. So these are the cations that I have drawn, and the anions I will be drawing in yellow. Okay. Now I am saying there is some mass and there is a particular volume, right? So the density is a particular value. Now if I am saying because of the defect, let us say one cation and one anion is missing from the lattice site. So I have just replaced one cation and I have replaced one anion. Now don't you think the mass which is present is reduced? So when the mass is reduced, you can simply say, na, the volume is same. So the density also will be decrease, right? That means because of Schottky defect, there is a change in the physical properties. But according to option number D, it says that there is no effect on the physical properties. So which is a wrong option. Okay. Now we are finally left with the third statement which I want to read for you. Statement number 3 says that trapping of an electron in the lattice leads to the formation of F center. And guys, this is not a wrong option. This is a perfectly fine correct option. Let me just take an example where the formation of F center takes place. You remember we have done one particular example that you take a sodium chloride crystal. So you have taken a crystal of sodium chloride and you heat it in the presence of sodium vapors. So what happens when you are heating the crystal of sodium chloride in the presence of sodium vapors? Let us say this is sodium chloride crystal. So we must be having positive and we must be having a negative here. Okay. Now what happens is when the sodium in the vapor state is heated, it will undergo ionization to form Na plus electron. Okay. So Na plus will also be formed and thus we will also get the formation of electron. Now in order to help the Na plus, one of the Cl minus, let us say this particular Cl minus will now leave the structure and will go to balance the Na plus, right? So it will form NaCl. But where will this electron go? And if one Cl from inside is going out, that means a vacancy is created here, electrical neutrality is disturbed. So this electron from outside will come and settle down here. And when the electron is coming and settling down here, this kind of position is known as F center. Right? And this is what the statement says. The statement says that trapping of an electron in the lattice leads to the formation of F centers. And yes, this is the correct statement. Okay, so for this particular question, question number 1, there were 4 options given to me. It was a multi-correct question. We found out that statement 1 is wrong, 2 is correct, 3 is correct, 4th is also wrong. Okay, so you need to take into account each and every single statement when you are talking about a question which is of multi-correct types. Okay. Having done with question number 1, now I think it's the time that we should be proceeding on to question number 2. So let me just prepare the board for you people. Okay. Moving on to question number 2 that we have. Oh, it's another category. It's a new category of question, and the question says that it's an assertion reasoning question. Like 4 options are given to you. One is A, B, C, D. In option number A, it says that statement 1 is correct. Okay. Statement 2 is the correct statement 2 is also correct. Okay. And statement 2 is the correct explanation of statement 1. So see, at the bottom of the question, he has given you 2 statements. So these are statement type questions. Statement 1 is given to us and statement 2 is also given to me, right? So we need to first of all figure out whether statement 1 is correct or not, whether statement 2 is correct or not. Then we need to figure out whether statement 2 is the correct explanation of statement 1 or not. And thus we can say, see here, option number B, statement 1 is correct, okay. Statement 2 is correct, okay. But statement 2 is not the correct explanation of statement 1. Third is statement 1 is correct, whereas statement 2 is incorrect. Fourth is statement 1 is incorrect, whereas statement 2 is correct, right? So now you understood how to attempt the question, but now let us first of all come on to the statements which are given to you. So the best way to deal with statement, assertion, reasoning type questions is that you should first of all take into account only and only statement number 1. So what does statement 1 say is that? It says that in any ionic solid Mx, so we have an ionic solid with the formula Mx, which is having Schottky defects. So you need to assume that Schottky defects are present in the ionic solid Mx. Okay. The number of positive and negative ions are same. Yes, that is correct. For example, if I would have started, let's say, with 100 positive charges and 100 negative charges, right? The overall compound would have been neutral. Am I right? Now let us say 3 positive charges are going away. So when I am saying 3 positive are going away, so we will be left with 97 positive, but there will be 100 minus. So there will be a change in the formula, but we know, right, that Schottky defect is a type of stoichiometric defect. Stoichiometric defect means there won't be any change in the stoichiometry of the compound. So if the formula earlier, let us say A plus were 100, B minus were 100. So the final formula was A 100, B 100. That means AB. Now if I am saying 3 cations have been lost from the molecule, so we will say 3 anions will also be lost, so that now the final formula will be A97, B97, which will end up giving you AB, right? So I think the statement number 1 that has been marked is 100% correct, okay? So when statement number 1 is correct, for sure we will ignore the option number D. Now either the answer can be A, B or C. Okay. Let us now try to read the second statement. Equal number of cations and anion vacancies are present. Yes, that is well obvious, no? For example, there is a crystal with 1, 2, 3, 4, 5, 6, 7, 8, 10 positive charges, okay? And now let us say I think something wrong I have done. So there must be a total of 10 negative charges as well. One extra I have created, right? So there must be a total of 10 negative charges as well. So how many positive were there? 10 plus. How many negative? 10 minus, right? Now let us say there is Schottky defect occurring. Schottky defect occurring means a cation and an anion will be missing. So one anion goes out and one cation will also go out, right? Now how many cations and anions are there? There are 9 positive, 9 negative, right? That is our statement number 1, that the equal number of cations and anions are present. But why so equal number of cations and anions are present? Because now you can say, right, that when one cation vacancy was created, in order to balance the charges, one anion vacancy was also created. So actually it was because of maintaining the neutrality, maintaining the vacancy, that equal number of cations and anions were missing, equal number of cations and anion vacancy were created, and that was the reason why that equal number of cations and anions vacancies are present, because of which we can say that the final number of positive and negative charges will also be same. That means statement number 2 is also correct. So it says that C option says that statement 2 is incorrect, which is wrong. So now either the answer can be A or B, but just 2 minutes back I told you that this is the explanation, right? So we will finally end up getting option number A as the correct option for this particular question. Okay. So this was about the second question that was there in the set for JEE Advanced. Now let us move on to the third question. But before I continue with the third question, let me just clear the board for you people. Okay, so question number 3. Okay, guys. So looking at this particular thing, you should not be confused. This is not a question, I mean, it is not such a big question. Actually, this question number 3, 4, 5, these are small questions, but they have been related to a passage which is given to you like this. So this is the passage type questions, another category of question. Let me start by reading out the passage for you. The passage says that in hexagonal systems of a crystal, that means I am talking about hexagonal close packing. So he says that in hexagonal systems of crystal, a frequently encountered arrangement of atoms is described as a hexagonal prism. That's it, nothing important. Here, the top and bottom of the cell are regular hexagon. So he's saying at the top of the cell, it's a regular hexagon, and at the bottom of the cell also, there is a regular hexagon. Okay, so this I am describing like this. Okay, it's a regular hexagon that I have drawn. Now it says that 3 atoms are sandwiched in between them. Okay, so what I'll say, one atom is there in the center surrounded by 6 atoms, right? Similarly, one atom at the center surrounded by 6 atoms, and 3 other atoms are present which are sandwiched between these 2 layers. Okay. A space filling model of this structure, which is also called as hexagonal close packing, which is HCP, is constituted of sphere on the flat surface which is surrounded in the same plane by 6 identical spheres as closely as possible. So see, he is saying there is one sphere in the center which is surrounded by 6 spheres, 1, 2, 3, 4, 5, 6 in the same plane. And guys, in my picture I have not shown you people in the perfect way, but you must be clear in your mind that all the 6 spheres will be touching the central sphere. And all the 6 spheres, they do also touch each other. Okay, so they are touching each other also, as well as they are touching the central sphere as well. Moving further, 3 spheres are then placed over the first layer so that they touch each other and represent the second layer. So see, you can consider this as the first layer and you can consider this as the second layer. Each of these 3 spheres touches the 3 spheres of the bottom layer. And then this is the third layer. So these 3 spheres are touching this also, these 3 spheres are touching the top layer also. Finally, the second layer is covered with a third layer that is identical to the bottom layer. So this is what he has described, right? So in this passage, he has just given you the description of what is a hexagonal close packed structure. Okay. Now let us finally look at the questions. This is the question given to me, and the question says that the number of atoms in one of this HCP unit cell is. This is the HCP unit cell that is given to me. Now I simply need to figure out how many total number of atoms are present. See guys, how should I be proceeding with the question? We need to simply calculate the total number of atoms. Which are present in the hexagonal cubic close packed structure. See, these 3 atoms, can you look at these 3 atoms? I am coloring them in blue color. 1, 2, 3. So these 3 atoms are simply present within the crystal structure. That means as a whole, their contribution will be 1. So 3 atoms are there present inside the structure. Okay. Moving further, can you see this atom, the one which I am coloring in white? This atom and a similar atom like this. So can you consider these 2 white atoms? So there are 2 such white atoms. And each such white atom is being shared by 2 unit cells. One on the top, one is the same one. And here also one is the same one at the bottom. So the contribution is 1/2. Plus, now guys, consider everything very carefully. I am asking you to consider the atoms which I am marking in pink. 1, 2, 3. This is the 4th one. This is the 5th one. This is the 6th one. 6 atoms in the top layer. 7th, 8th, 9th, 10th, 11th, 12th. That means there are 12 such pink atoms. What is the contribution of each pink atom in the hexagonal close packing? This is what we need to find out. See guys, if I am drawing the thing once again, I will not draw the complete picture. I will just draw whatever is required. Okay. Can I consider another unit cell which is yellow in color just besides the given unit cell? Right. Also, can I consider another unit cell which is blue in color, which is also besides the given unit cell. Something like this, right? Now I am asking you to consider the pink atom. Okay, don't you think if you take this as the center, 1/3 of the atom is becoming a part of the white unit cell. So like 1/3 of the atom is becoming the part of this white unit cell. Another 1/3 part of the atom is becoming a part of this blue unit cell. And another 1/3 is becoming a part of this yellow unit cell. Am I right? But guys, that means this particular atom is sharing 1/3 to the yellow one, 1/3 to the blue one, and 1/3 to the white one, right? But don't you think I can draw one more unit cells? Like for white, let me draw the dotted lines, showing that there is a similar white unit cell in the above plane, right? Can I now draw another blue lines showing that a similar unit cell is there in the above plane, right? And similarly, can I draw a yellow unit cell in the above plane, right? That means this atom is present only 1/6 in one unit cell. So 1/3, see, there is one atom. First of all, you divided it into 3. Okay, so making it the contribution 1/3. Now, not only this, then you said half of it is present in the above, half is present in the bottom unit cell. So further you are dividing it by 2, making the contribution 1/6. Okay, and there are 12 such atoms, each with a contribution of 1/6. Now finally, if I ask you to calculate, you will be getting 3 into 1 as 3, 2 into 1/2 as 1, and 12 into 1/6, and this will make a total of 2. So making it a total of 3, 4, 5 and 1, 6. That means the first question, the third question that we were having, the number of atoms in one of this HCP unit cell is 6. So there are not 4, there are 6 atoms which are present per unit cell in the case of hexagonal cubic close packed structure. Okay, so this was one part of the question. Now we need to move on to the second part of the question, which is the fourth question. Let me prepare the board first, and let us not remove anything. Moving on to the next question that you have is question number 4. The question says that you need to calculate the volume of this hexagonal close pack unit cell. So if it would have been a simple cubic close pack, then the volume would have been A cube, right? But then it is hexagonal close pack system. And if you are talking about hexagonal close packing, see very carefully again. This is something like this. Something like this. Am I right? So if the edge length I am considering to be A, the B is also considered to be A. This is a hexagon, whereas the height is considered to be H. Okay, so what should be the volume of unit cell? So can you guys simply say that the volume of unit cell is, so we need to find out the volume of this unit cell. So the volume of unit cell is area of base into the height. So which will be area of base to be multiplied by height. Okay, so when I am talking about area of the base, what should be the base considered? Start connecting all the vertices of the hexagon to the center. Don't you think you are getting 6 equilateral triangle, each with the edge length A? So if the edge length is A, now you can write area of base is 6 into area of equilateral triangle multiplied by the height h, right? So now what should be the area of the triangle? You have each triangle that is given to you. Let us consider any such triangle OAB. I am just numbering it as O, any one as A, any one as B, okay, with the edge length equal to A. So what should be the area of the triangle? That is 6 into root 3 by 4 into A square multiplied by the height h. This is the volume. But let us see, the volume here is in terms of r cube, right? But we don't have anything in r. Now consider one thing again. I am saying in the case of hexagonal close packed structure, the thing which looks like how you actually see it, it's a triangle, and then all of them are touching each other. So something like this, and one is there in the center. Like this you will draw others also, right? That means you can simply say, if this is r, then the edge length is equal to 2r, okay? So we know that A is equal to 2r. Finally, I can figure out that the area of the triangle will be 6 into under root 3 by 4 into 2r whole square multiplied by h. But then also I am not satisfied with the formula because I don't have a connection between h and r. So either I need to find out the connection between h and r, or I need to find out the connection between h and a, so that I can finally substitute it here in the terms of r. Right? Okay. Now moving further, how to find out the connection between h and r? Guys, see, you do agree, right, that 6 atoms are present somewhere here, and one is there in the center. Similarly, 6 atoms are present somewhere here, and one is present in the center, right? Now we know one more thing, that 3 atoms are present exactly in the half of the unit cell. That means at a distance. So guys, let us call this height as c. Okay, so at a distance of c by 2, these will be present. Okay, moreover, I can say that when you are placing these 3 on the top of these 6 atoms, it is gonna form a void, right? And these 3 atoms are gonna touch these 6 atoms. Similarly, these 3 atoms will also be touching these 6 atoms. Okay, so what I'll say is, you consider this atom A. The one I am circling in yellow, this is the atom A. Okay. Now I am drawing it once again. So this is atom A, this is atom B, and this is in the center atom O. Okay. Let us do one thing. I am asking you to draw a perpendicular from A to OB, named as AA dash. Okay. I am asking you to draw a perpendicular from O to AB, and I am calling it as OO dash. Fine. You know, right, this angle is 60 degree. So half of the angle will be 30 degree. So this is what we got as 30 degree, right? Now I am asking you to consider a triangle A dash B. That means what I am asking you to consider a triangle which is 30 degree here, 60 degree here, 90 degree here. See, 90 plus 30, 120 plus 60, 180. So this triangle is confirmed. Now 30 degree thing is with A, 60 degree thing is with B, and then this 90 degree thing is with A dash, right? And now I am asking you to calculate the value of cos 30 degree. Let us see how we are doing. So from this particular figure, if I ask you to calculate the value of cos 30, which is under root 3 by 2. Cos 30 is written as base by hypotenuse. So cos 30 is, cos is base by hypotenuse. So what is the base? Base is AA dash, you can write it AA dash, divided by what is the hypotenuse? Hypotenuse is AB. The hypotenuse is AB. Am I right? And guys, what is the value of AB? The value of AB is A, which is the edge length, right? So can I now simply say that AA dash divided by A is equal to root 3 by 2? Also, can I now simply say AA dash is equal to root 3 by 2 times A? Fine. That means I simply got the value of AA dash. What is AA dash? This is AA dash. Okay. Also listen to me very, very carefully. Let us call this intersection point as X. Okay. I am just calling the intersection point as X. So when I am calling this intersection point as X, can you say, look into this figure if you can see. One is AA dash, one is BB dash. So this point is X. This point I am representing it as X. Okay. Now can you simply find out what is the value of AX? See guys, when two perpendiculars in the equilateral triangle intersect each other, at the point of intersection, the perpendicular is divided in the ratio 2:3. That means I can say that, okay, let me remove this. So I can simply say that AX divided by AA dash in the ratio 2:3. That means the value of this AX to be divided by AA dash is 2/3. I don't know what is the value of AX. This is equal to 2/3 into AA dash. Fine. Putting up the value of AA dash, which is equal to 2/3 into under root 3 by 2 A. Fine. Let us see what is the value of AA dash that you are getting. So 2 and 2 will get cancelled. So we get A by under root 3. So we will get AX equal to A by under root of 3. See guys, once again, this value AX is A by under root 3. Okay. Now, listen to me once again, that too very, very carefully. I said that this height from the center of this layer to the bottom layer is C by 2, right? I am asking you to draw. Let me draw this figure for you people once again. So we just need to know that everything is written here. Let me draw the figure once again so that you can easily understand everything. So see guys, see once again, this is the whole thing with the height C. I am not drawing the whole thing. I will just be drawing this half portion. Maybe this bottom half or top half. Okay. I am just enlarging this particular portion. See what is to be done. So I've got something like this and I connected the vertices, and finally I am getting this as A, or let me even draw it in a bigger fashion so that the things are clear. So let me call it as A, let me call it O, let me call it B, right? Also what did I do? I have drawn AA dash somewhere here, I have drawn OO dash somewhere here, right? And the intersecting point I called it as X. This point is X. Also you know the length of this AX, which is A by under root 3, right? Now moving further, what did I say? I said at a height C by 2. So there is one circle here, one circle here, one circle here, and at the position C by 2, this and this circle are touching each other, right? I cannot show it in the 2D, but then yes, they are touching each other. So if you draw the center of this circle C, we know that, so let us draw it to the line X. So I am asking you to consider it with the point X. So at this point X, it will be touching. That means this point X can be considered to be at an angle of 90 degree. Okay, and this value is C by 2. Okay, half the length of C, and now we have this like this. So this is point number C. Clear enough? Everything is cool till here. So once everything is cool till here, now I will ask you to consider the triangle ACX with angle AXC equal to 90 degree. Okay, AXC is equal to 90 degree. Now guys, see what I said. I am saying if a sphere is placed here and this particular sphere, these two will be touching each other, and when the two will be touching each other, this will be equal to R plus R, right? So the value of AC. Now guys, consider the triangle ACX. Let me remove everything. Finally, I am asking you to consider the triangle ACX. So when you consider the triangle ACX, it is something like this. This is equal to 2R again, and this value is given to us as, this is 90 degree, and this value is given to us as A by root 3, and this we need to find out, right? Okay. Now guys, we know that this is 2R, or 2R can also be written as A in order to simplify. Now I can use Pythagoras theorem, and I can say that A square minus A square by 3 is equal to CX whole square. That means under root 2 by 3 times A is equal to CX. But the length of CX was C by 2. Height was H, complete H. So I need to take the double. So what should be the final height? The final height will be 2 times C. And what is 2 times C? It should be 2 times under root 2 by 3 times A, which is nothing but under root 8 by 3 times A. Finally. So finally we got the value of height as H, and now I can substitute the value. So this will be under root 8 by 3 times A. Okay. So guys, although now see, the entire problem lies in order to figure out what is the height of the hexagonal closed packed unit cell in the terms of H length A, right? It is not easy to derive the whole derivation, like to derive the whole formula in exam. So it's better that you people can remember the direct formula for the height. Okay. Once you know the direct formula of the height, you can directly substitute it here, and once you will be substituting it here, the final answer, if you calculate, will be something around 24 under root 2 R cube. You can calculate and you will finally get the answer as 24 under root 2 R cube. Let us see if there is a answer like that. So we have 24 root 2 R cube is the correct answer. Now don't be afraid that these kind of questions, like don't think that this was such a lengthy question so it will not be asked in exam. This is a past year JEE question, JEE advanced question. It has already been asked in your exam. That means you should directly know the value of height. Once you know the value of height, it is easy to calculate the volume also. Okay. Fine guys, so please note it down so that we can continue further to the next question as well. Okay guys, so having done with this particular thing, let me now move on to the next question. I do not want to rub anything on board since the 5th question is also the paragraph question. And the question is, what is the empty space in this hexagonal closed packed unit cell? So we need to calculate not the efficiency but the empty space. But this is a direct question, right? In the case of hexagonal closed pack unit cell, you would have marked up, right, that the efficiency is 74%. So if efficiency is 74%, which is same as FCC, right, or CCP. So what will be the empty amount? So empty space will be 100 minus 74, that will come out to be 26%. So option number D. Now for those who do not remember how to calculate this 74, now also this will be very easy for us. See? We know, right, how to calculate the packing fraction or the packing efficiency. Packing fraction is basically calculated as volume occupied divided by the volume available. To be multiplied by 100. Am I right? So when I am talking about the volume occupied is nothing but the number of atoms. So it should be number of atoms multiplied by volume of one atom, which is 4 by 3 pi r cube. To be divided by the volume available. See, the volume available we just calculated in the previous question. To be multiplied by 100. Right? Now if you are planning to calculate the number of atoms which are available in the case of hexagonal closed pack structure. You remember, right, we have done the third question. See? The third question was you need to calculate the number of atoms in one of the HCP, and I remember the answer was coming out to be 6, right? So when the answer is coming out to be 6, so the final answer will be 6 multiplied by 4 by 3 pi r cube to be divided by 24 root 2 r cube multiplied by 100. So if you solve it, you will finally end up getting the value equal to 74%, and thus the empty space that will be present is 100 minus 74, that is 26%. Okay? So guys, this was about our, okay, not this one, but yes, so this was about our fifth question. So now we are done with half of the exercise for JEE Advanced. I want you to note it down, take a break so that you can finally get to know if there is some doubt or something, revise it again so that now we can move on to the next question. Note it down, please. Okay guys, I think every one of you is now done with question number 5 as well. Having done this much, now we need to move on to question number 6. But let me just clear the board for you. So let's see what is said to us in this particular question. The question says that, oh, it's match the following question. The question says that match the crystal system or the unit cells which are mentioned in column number 1 with their characteristic features which are mentioned in column number 2. Okay. So column 1 is given, column 2 is given, A, B, C, D 4 options are given, P, Q, R, S 4 options are given, right? Now how we are gonna move forward? This is simple cubic and face centered. So we need 2 unit cells, which is simple cubic and face centered. We need cubic and rhombohedral. We need cubic and tetragonal. And we need hexagonal and monoclinic. That means we need all the crystal systems. So why not, let's do one thing. See guys, he will not be asking you the questions from that table. You remember we have done one table. So those table questions will not be asked for like 4 marks or something. But this question is quite lengthy and it is of a good weightage. So now he can ask you those questions from the table. So you remember, right, we have done that CTO matri hai. I gave you this mnemonic, right? And this was written as CTO, MT, R and H. So 1, 2, 3, 4, 5, 6, 7 crystal systems we have drawn, right? How we have written? Let me just write it down once again. So we started with cubic, a big line, right? Then we have tetragonal, C, T. Then we have orthorhombic, O. Then we have monoclinic, Ma. Then we have after this triclinic, the. Then we have rhombohedral, and finally we have the last one, 1, 2, 3, 4, 5, 6, 7th, which is hexagonal unit cell. Right? So we had written all the 7 crystal systems. The names of all the 7 crystal systems I have written. After that, what have we done? We will just make a line like this. And we will write 0, 1, 2, 2, 2, 0, 1. Right? Then we'll say what is to be done. So we will simply write A equal to B equal to C. Then we have finally we have and the next one we have, that's it, right? So we'll say 0 means all are correct, 1 incorrect, 2 incorrect, 2 incorrect, 2 incorrect, all are correct, 1 incorrect, right? So this is 0, 1, 2, 2, 2, 0, 1, and here we can figure out this thing. Now we need to come on to the angles. How we are going to talk about the angles? We'll say alpha is equal to beta is equal to gamma is equal to 90. Point number 1. Alpha equal to beta equal to gamma equal to 90. Alpha is equal to beta is equal to gamma equal to 90. Right? Then you remember I asked you that you need to switch on to the last one. Alpha is equal to beta is equal to 90, whereas gamma is equal to 120. After that I asked you to again go back to the previous one. So this is alpha equal to gamma equal to 90. Whereas beta is not equal to 90, right? Then I said this is nothing, right? All are wrong. So we'll say alpha not equal to beta, not equal to gamma, not equal to 90. Now we are left with the last one where A is equal to B is equal to C. So simply write alpha equal to beta equal to gamma equal to 90. But then this and this first one will be same. So you need to make a little difference. So simply say alpha equal to beta equal to gamma, but all of them are not equal to 90, right? So if anyhow other you remember this particular table, now let us try to figure out the answers to the options A, B, C, D. A can have all the 4 options or any 1, any 2, any 3, whatever. Okay, let us see guys what is to be done. Option number A says he is talking about simple cubic and face centered cubic unit cell. That means talk about simple cubic and the face centered cubic unit cell. Okay guys, see carefully. I am talking about simple cubic and face centered cubic unit cell. So guys, whatever you say, simple cubic, these are nothing but cubic unit cells only, right? Look at the options. Options are these have the cell parameters A equal to B equal to C and alpha equal to beta equal to gamma equal to 90. So cubic are A equal to B equal to C, alpha equal to beta equal to gamma is equal to 90. Right? So for option number A, we will first write PQRS. Out of all, P is correct. Okay? Moving on to option number Q. These are two crystal systems. No, yaar, this is same, no. Simple cubic, the crystal system is cubic. Face-centered cubic, the crystal system is again cubic, right? So Q is not the correct option. They are not different crystal systems, they are the same crystal systems. Moving further to our option, they have only two crystallographic angles of 90 degree. Are they having two crystallographic angles of 90 degree? Let's see. Alpha is 90, beta is 90, gamma is 90. Three crystallographic angles are 90 degree, right? Not two. So even R is not the correct option. Okay. Moving on to S. They belong to the same crystal system? Yes. So they actually belong to the same crystal system, which is the cubic unit cell. So even S will also be the answer. Okay. So I can very easily move on to the question and I can say that for option number A, there are two answers. One is P and one is S. Okay. Now we move on to the second part, which is part number B. He is talking about cubic and rhombohedral. So let us move on to, this is cubic which is given to me, and where is rhombohedral? This is rhombohedral. So these two are given to me. Let us try to figure out the PQRS once again. So we have cubic and rhombohedral unit cells. And we have the options. Let us start one by one. The very first option says that these have cell parameters A equal to B equal to C and alpha equal to beta equal to gamma equal to 90. Cubic is having A, B, C, alpha, beta, gamma 90. Okay. Rhombohedral is having A equal to B equal to C, alpha equal to beta equal to gamma, but not equal to 90. That means they are not same. So P is wrong. Further moving on to B, option number Q. These are two different crystal systems. Yes, this and this. These are two different crystal systems. So Q is the correct option. Option number R. They have only two crystallographic angles of 90 degree. Cubic is having three crystallographic angles of 90 degree. So again a wrong option. The S says that they belong to the same crystal system. No. Right now we said that they belong to two crystal systems. Here it is saying they belong to same crystal system, which is a no. Right? So for option number B, the only correct answer that I got is answer number Q. Okay? Done? Let us now move on to option number C. Let's see what is there in the third option, which is cubic and tetragonal. Let us move on to cubic and tetragonal. These two. So when I am talking about cubic and tetragonal. Okay. So cubic and tetragonal, first of all, so this is C option, PQRS. What am I saying? These have cell parameters A equal to B equal to C, alpha equal to beta equal to gamma 90. So cubic is having the same. Tetragonal is having A equal to B not equal to C. That means even this is wrong. Okay. Then these are two different crystal systems. Yes, these are two different crystal systems. R says that they have only two crystallographic angles of 90 degree. No, cubic is having three. So even this is wrong. And S says that they belong to the same crystal system. No, they belong to the different crystal system. Okay. So for option number C also we did exactly the same way and we finally got the option as option number Q. Okay. Having done this, let us now finally move on to the D part, which is hexagonal and monoclinic. So where is our D part? We have hexagonal and we have monoclinic. So let us see what is there in hexagonal and monoclinic. Hexagonal and monoclinic. Which is option number D. Okay. So first of all it says that they have cell parameters A equal to B equal to C, alpha equal to beta equal to gamma equal to 90. Monoclinic, A not equal to B not equal to C. Let us not go to hexagonal because monoclinic even doesn't satisfy. So P is wrong. Okay. Moving on further, we have these are two different crystal systems. Yes, 1 and 2. Yes, these are two different crystal systems. Moving on to the third one, they have only two crystallographic angles of 90 degree. Let us first talk about monoclinic. Alpha and gamma are 90 but beta not equal to 90. Yes, good enough, right? So only two of them are having 90 degree. Move on to hexagonal. Alpha and beta are 90. Yes. Whereas gamma is equal to 120. That means not 90. So even we can say that R is correct. And option number S says that they belong to the same crystal system. No, they belong to different crystal systems. So even option number S is wrong. So for option number D, we ended up getting the values as Q and R. Okay. So I think, see, the main point about the question, if you would have learned how to remember the table which I have shown here, it would have been very easy for you to get full marks for this particular question, right? However, if you would not have remembered the table, it would have been really very difficult because then you would have to mug up for cubic, for rhombohedral, for monoclinic, for hexagonal, tetragonal and blah blah blah. Okay, so it's better to know some way. Maybe you can design some other significant way in order to memorize the table. That will also be very helpful. Okay, so having done with this, guys, let me clean the board for you so that we can finally move on to our next question. And this next question that we'll be doing is question number 7th. So I have tried my best to take up all the different pattern questions for you. Like we have done match the following, we have done assertion reasoning, we have done single correct, we have done multi correct. Other types are also there. So let me show you those particular types as well. Moving on to question number 7th. Let's see what is there in question number 7. It says that in the FCC unit cell, point number 1. So we have a face-centered cubic unit cell. So when I am talking about a face-centered cubic unit cell, that means atoms will be present at the corners plus at face centers. Okay. He is saying what fraction of the edge is not covered by the atoms. He is simply talking first of all by edge. What do we mean by edge? Edge means where the two faces will intersect, right? Where two faces will intersect each other. So this intersection line is known as edge. And my question is, what fraction of edge is not covered by the atoms? So guys, can I draw the face-centered cubic unit cell something like this? So that is the face of the cube that I'll be drawing. Let me draw it again. An atom is there in the center. Something like this I have drawn. So 4 of the spheres are present at the corners of the unit cell. So we can say 1, 2 and 1 will be 3. The diagram could have been more symmetrical and the 1 is 4. Right? Now we need to basically figure out. Let us just give them names. Okay. Let us consider the edge length equal to A. But you can see, right, this blue portion is not covered. So we need to figure out the length of this blue portion, but in the terms of ratio, what fraction of edge length is not covered. So this is the same blue area. Length, I should say, not the area. Similarly, here we have this blue length and here we have this one. So because of like unsymmetrical drawing, you can see they may be different in sizes, but then if you draw them symmetrically, the blue lengths will be same, right? So we need to figure out this blue portion. Let us call it to be A dash and B dash. Okay. So finally I need to figure out the value of A dash B dash divided by AB. Fine. Considering the radius of the sphere as R. Okay. So guys, can you say that the length AB can be written as R plus A dash B dash plus another R, right? So you can say AB is what? A is equal to 2R plus A dash B dash, right? So I can simply write A dash B dash is equal to A minus 2R. What I need to calculate? A dash B dash divided by AB. So A dash B dash divided by AB will be A minus 2R divided by AB, edge length is A, right? But we won't be able to get the answer until and unless we know the relationship between A and R. But we know that this is face-centered cubic unit cell. So I can ask you to consider the diagonal of the face. Okay. Consider the triangle ABC, where angle B is 90 degree. Right. So can you apply Pythagoras theorem? AC whole square will be equal to A square plus A square, which can be written as 2A square. That means AC will be written as under root 2A, and under root 2A can be taken as R. Root 2A is equal to 4R. So finally we got the value of 4R. So you can say no, 4R is equal to under root 2A, right? So you can say 2R into 2 is equal to root 2A. What will be the value of 2R? A by root 2. Substitute the value here. So you will get A minus 2R will be A by root 2, 2b divided by A. Am I right? So you will get the value as under root 2A minus 1 divided minus 1 times A divided by root 2A. Cool enough? So now we have root 2A as 1.414. 1.414 minus 1 is 0.414. A to be divided by under root 2 is 1.414. A got cancelled. If you solve it, you will end up getting the value as 0.293. Let's see if there is an answer like this. 0.134, no. 0.24, no. 0.293 has been given the correct answer. See guys, if the question would have been, let's say if this would not have been there, but if it would have been 0.38 or something, let's say some other value, okay. So then you would have said even 0.24 could be taken as a correct answer, okay. But when the values which are given to you and none of these is also mentioned, so you need to be very careful about the exact calculation, because 0.24 is different and 0.293 has been taken differently, right? So you need to go to the exact calculation of the answer. Okay guys, so I think with this particular thing we are done with our question number 7 as well. Now we'll do one thing. Let us directly move on to the another question, which is question number 8. But again, for that I need to clean the board, so give me a minute. And let us see. So guys, this was another category of question where we have just taken it as simple, single correct answer, right? So this question was the normal traditional questions which is asked in JEE. Now if I move on to the next question for the exercise. Okay, it's a good question and it's another type of question that is known as integer type question. So the answer can be either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. No points, nothing. The question says that silver atomic weight is given to be as 108 grams per mole. So we are given silver atom and the atomic weight is given to us as 108 grams per mole. Okay. Moving further, it has been given a density of 10.5 grams per cc. Okay. The number of silver atoms on the surface area of, so there is a particular surface area which is given to me, which is 10 raised to the power minus 12 meters square. And you need to calculate how many total number of silver atoms are there on the surface area of 10 raised to the power minus 12 meters square, and you need to express them in the scientific notation as y into 10 raised to the power x. And I have asked you to simply calculate the value of x. What is the value of x? This is what we need to calculate. Okay, the question is you need to calculate the total number of silver atoms. The question is actually a very good question. So let us try to move into the detailed solution of the question. The question starts like we are given something as the formula of density, right? So you know now that we can say density is equal to A into Z to be divided by N naught into A cube. Whether you calculate the density of a small portion of the unit cell or one complete unit cell or the entire the crystal structure, the density is going to be same. It is an intensive property, right? So we can say density is equal to A into Z to be divided by N naught into A cube. Let us substitute the values. The values that are given to me are, so 10.5 grams per centimeter cube. Do take care of the units, okay? Is equal to, what is A? A is the mass number. So the mass number that is given to me as 108 grams per mole. Always mention the units besides the numerical value. Now what is the value of Z? Okay. So you people know, right, that silver atom is known to crystallize in face-centered cubic unit cell. This we have done in so many questions. So if it is there in face-centered cubic unit cell, you can say it is present at corners plus it is present as face centers. Now see, if it is present at corners and at face centers, you can say 8 corners with a contribution of 1 by 8 plus how many face centers are there? 6, each with a contribution of 1 by 2, making it a total of 4. That means the effective number of atoms per unit cell is 4. To be divided by N naught. N naught is Avogadro's number. So which is 6.022 into 10 raised to the power 23 mole inverse. Guys, do not forget to put the units. Avogadro's number is 6.022 into 10 raised to the power 23 mole inverse. That is why this mole inverse and mole inverse will get cancelled. Okay? Into multiplied by A cube. See? So what will I say? Gram and gram will get cancelled. Mole inverse will get cancelled. So final answer we will get either in centimeters or you can convert it in meters. So if you calculate, you will end up getting the value of A as 4 into 10 raised to the power minus 10 meters. Okay, so this is what we have got the value. Now moving further, he simply was talking about the surface area, right? He was talking about surface area and we have considered that silver is present in face-centered cubic unit cell. That means it's a cubic unit cell. Although it's a cubic unit cell, so if I'll say that the edge length, so this is what the edge length we have got, no? So edge length is A. So what should be the surface area of the unit cell? So you can say, so surface area of unit cell will be, you can call the surface area of unit cell to be A square, so which will be equal to 4 into 10 raised to the power minus 10 meter whole square, which will come out to be 16 into 10 raised to the power minus 20 meter square, which finally can be written according to scientific notation as 1.6 into 10 raised to the power minus 19 meter square. Why did I write it as 1.6 into 10 raised to the power minus 19 and not 16 into 10 raised to the power minus 20? Because in the question he has specifically mentioned that you are going to talk about scientific notation, right? So I am following the same things and we finally obtained an area of 1.6 into 10 raised to the power minus 19 meter square. Okay? Moving further, can I now say that, see guys, can I now say that the area of one unit cell is 1.6 into 10 raised to the power minus 19 meter square, right? Or can I also say this to be like this, that if you have 1.6 into 10 raised to the power 19 meter square area occupied. So if this much area has been occupied, how many unit cells will be there? You will be having just one unit cell. But if I am saying that 1 meter square area has been occupied, how many unit cells will be there? You can simply say, ma'am, 1 divided by 1.6 into 10 raised to the power minus 19 unit cells will be there. But do I have 1 meter square area? No, I do not. How much meter square area I have? I have a total of 10 raised to the power minus 12 meter square area, right? So if just use the unitary method, if 10 raised to the power minus 12 meter square area has been occupied, then how many unit cells would have been present? So the number of unit cells that will be present will be 10 raised to the power minus 12 to be divided by 1.6 into 10 raised to the power minus 19 unit cells. Let me just enclose it in the bracket. And if I am asking you to solve it, you will end up getting the value 6.25 into 10 raised to the power 6. Oh my God, these many unit cells will be present, okay? But guys, the question was, read the question again. You were to find out the total number of silver atoms present, right, in this particular area. Where did I come up to? I just came up to one particular point, that the total area occupied is 10 raised to the power minus 12 meter square. Right? Now we need to continue further in order to find out the total number of atoms which are present in that much unit area. Note it down so that we can continue further. Okay guys, so having done with this particular value that I have asked you to remember, let us continue further. Finally, we ended up our discussion by saying that we got a total of 6.25 into 10 raised to the power 6 unit cells, right? But my main concern was not to find out the total number of unit cells. My main concern was to find out the total number of atoms in that particular area, right? I am talking about face-centered cubic unit cell, no? So let us see carefully once again. Let me just erase what all I don't need. See, so we are considering the face-centered cubic unit cell. This is the kind of face-centered cubic unit cell where one atom will be present in the center and there will be atoms which are present here, here, here and here. Like this is how the face will look like, right? 4 atoms will be there and then 1 atom is there in the center. See here once again carefully. So if I am asking you to take an approximate total, see guys, listen to me very carefully. We are talking about surface area. We are not talking about volume. When you were talking about volume, we used to say in the face-centered cubic unit cell, the atoms will be at the center of faces plus they will be at corners. Right? So we used to consider 8 corners with a contribution of 1 by 8, 6 faces with a contribution of 1 by 2, making it a total of 4. Right? But now I am just considering a surface area. We are just considering this particular thing, the surface area. And when I am considering the surface area of a face-centered cubic unit cell, what will I say? I will simply say it occurs as if one atom is there in the center and there are 4 atoms which are touching the given atom. But I am just considering the surface area. That means I am assuming it to be a 2-dimensional thing, right? So how many atoms are present? 1 by 4th of this atom. So 1 by 4th we have got, plus another 1 by 4th of this atom, the one which is there in yellow, plus let us say this pink atom. This is present whole in one go. That means 1 plus another yellow atom, which is again 1 by 4th of the entire surface area, plus we are getting another 1 by 4. making it a total of approximately 2 atoms, right? So in one particular unit cell's area, on the top there are approximately 2 atoms present. So see guys, here we got the total number of unit cells, but in one unit cell I told you there are a total of 2 atoms. So if I multiply it with 2, so these are the number of atoms. Okay, so once I am asking you to multiply it with 2, you will finally end up getting the value 1.25 into 10 raised to the power 7 atoms. I have written it in scientific notation. Okay, so it should be 12.5, right? But 6.25 into 2 is 12.5. But write it in scientific notation, which is 1.25 into 10 raised to the power 7, right? Now come here. So he is saying that the value is expressed as y into 10 raised to the power x. So it is 1.25 into 10 raised to the power 7. What is the value of x? 7. Okay, so don't mark the answer as complete 1.25 into 10 raised to the power 7. No, that's not the answer. Our required answer is to only tell the value of x, which is 7. Good enough? It was a very, very good question because almost all the concepts like silver lies in face-centered cubic unit cell, using the formula of density, then calculating the number of atoms which are there in the square closed packing, right, in the face-centered but two-dimensional. So this was one of the very, very good question which was asked in JEE advanced paper. Now having done with this, let us move on to the next question, not the last but the second last question. That is question number 9. So another type which I was mentioning, the integer type, that is also done. Almost we have covered all the different types of questions that have been asked in JEE Advanced from this chapter. Okay, let us move on to the next one, which is 9th question. Again the question says that which of the following statements are correct. It is again a multi-correct question. Let's see. The coordination number of each type of ion in CsCl crystal is 8. So we need to figure out whether the coordination number of ions in the unit CsCl is 8 or not. How do we do this? We know, right, in the case of cesium chloride, Cl minus are present in the primitive unit cell. Right? A primitive unit cell means the atoms are present only and only at the corners. So when atoms are present only and only at the corners, this atom is in direct touch with 8 chloride ions. How? See, listen to me very carefully. And the cesium plus will be present in the body center void. Listen carefully. When cesium is present in the body centered void, that means I can say, right, cesium is in direct touch with 4 chlorines on the top face. 1, 2, 3, 4 and 4 chlorines at the bottom face, right? That means cesium, this pink atom, is in direct touch with 4 yellow atoms on the top, 4 yellow atoms at the bottom. So cesium is having a coordination number of 8. Right? Now how to remember this? See, so we know that cesium and Cl are in the ratio 1:1. So if the coordination number of cesium is 8, then the coordination number of chlorine will also be 8. So the option is correct, that is for sure. But how to figure out whether the coordination number of Cl minus is 8 or not? See carefully. Consider any particular unit cell again. Where one chlorine atom is present in the center of the body. Okay, and I am considering one cesium atom is present in the center of the body and all the chlorine atoms are present at the corner. Okay, that means this corner chlorine atom, which I am making yellow in color. So this corner chlorine atom, which I am drawing as yellow in color, this is in direct touch with this body centered cesium, right? How many such cesiums will be present? So we need to simply find out how many such cubes this chlorine is actually a part of. This chlorine is a part of this blue cube, 1. This chlorine must be a part of yellow cube, number 2, right? That means there must be one cesium atom in the center of this yellow box also, which this chlorine should be directly touching, 2, right? Now the same chlorine must be a part of another cube as well, something like this, which is there at the back of the yellow one, and another cesium must be there in the center. And this chlorine must be directly touching this also. So cesium number 3, right? There must be one another pink cube which I am drawing like this. So this pink cube will also be present there, and there also there will be a cesium atom. And the central chlorine will be in direct touch with this as well. Okay? And finally we will say draw another blue cube on the top. And when you are drawing another blue cube on the top, there must be one cesium here. So 4 were there in the same layer, and similarly you can say there will be 4 in the top layer. For example, for the yellow one, you can draw. Similarly for the white one also, you can draw, right? And for the pink one also you can draw. So making it a total of, so this is for white one, and this will be the next blue one. That means if you are looking at the Cl atom which is there in the corner, it is in direct touch with 1, 2, 3, 4, 5, 6, 7 and 1, 8. So 1, 2, 3, 4, 5, 6, 7 and 1 is there at the bottom. So see, 4 are there in the top and the yellow one is left, so which I am drawing as this one. So 4 are there in the top and 4 are there in the bottom. So each Cl is also surrounded by 8 cesium. Fine. So you can say that the coordination number of Cs and Cl is 8. That is correct option. Fine guys. Moving further, we have a metal that crystallizes in BCC structure has a coordination number of 12. This is wrong, no? This is what I said. If there is any atom in the center, it must be attached to 1, 2, 3, 4. 4 on the top, 1, 2, 3, 4. 4 on the bottom. So it should be having a coordination number of 8 and not a coordination number of 12. So option number B is wrong option. Okay. Moving further, a unit cell of an ionic crystal shares some of its ions with the other unit cells. That is perfectly okay, right? See, so there is a unit cell of an ionic crystal. I am considering this blue unit cell. Don't you think this Cl is a part of this blue unit cell? Along with this, the Cl is also a part of the yellow unit cell. Right? So this is quite possible that if there is any particular atom in the unit cell, it might be shared with the other unit cell as well. So this is also option number C, that is correct. Okay. Moving further, we have the edge length of the unit cell in NaCl is 552 picometers. Let us say how. The radius of Na plus is given and the radius of Cl minus is given. Let me just note down the value. Radius of Na plus is given to me as 95 and the radius of Cl minus is given to me as 181. And we need to calculate the value of edge length of NaCl. You know, right, in the case of NaCl, Cl minus are present at corners plus they must be present at face centers. And Na plus will be present in octahedral voids. And where are octahedral voids present? The octahedral voids are actually present at the edge center. Okay, so how will the final molecule look like? So guys, these white ones are the Cl minus that I have represented, and the yellow ones are the Na plus because these are present in the edge centers. Fine. So can you consider the radius of Cl minus plus the radius of Na plus Na plus Cl minus. That means I am asking you to consider 2 times 181 plus 95. If you calculate, it comes out to be 2 times, and then finally we will get 276. So yes, the answer is 552 picometers. Let's see. He is saying the answer is coming out of the edge length as 552 picometers, which is correct, correct, not correct, correct. Okay. So guys, this was all about question number 9. Let us now finally move on to the next question. And the next question that we are gonna discuss now is question number 10. So let us see what this last question is asking you people to do. So may it be an easy question, may it be a difficult question, let us try to figure out the answer. And the question says that the packing efficiency of a 2-dimensional square unit cell, which is shown below. So this question we have exactly done in the, I think, question number, that silver atom question, which was question number 8, right? The same concept we'll be using once again. You need to calculate the packing efficiency. See guys, if it would have been a 3-dimensional unit cell, then the packing efficiency would have been given by volume occupied to be divided by volume available multiplied by 100, right? But since we are talking about a 2-dimensional square closed packing, so the packing efficiency will be given by area occupied to be divided by the area available multiplied by 100, right? What should be written as the area? So 1 is there in the center. We have 1 like this. We have 1 like this. We have 1 like this and 1 like this, right? Let us consider the edge length as A. So the area available is A square multiplied by 100, and what is the area occupied? C. So this is what we have just done. Let me write it again. So 1/4 of the area of this circle plus drawing all the circles and coloring them, I really feel like eating pizza. I think you must also be feeling the same, right? So I'm just imagining I am having a double cheese and then another one. This one and this one. So first I'll take 4 slices from all my friends. Okay, this is free of cost, and then I will eat 1 complete pizza from my side also. Oh my god, I will have 2 pizzas. And I will give 1 or 2 to other people also. So let me just color, because it is mixture of all the vegetables which are there. Corn is there. So what is left? Mushroom is left, and I added everything, right? So making it a total of, what is the area? 1 plus 4 into 1 by 4. That means 1 plus 1, 2. So area of one circle is pi r square. So it will be 2 into pi r square. Okay. So area occupied will be 2 into pi r square. Divided by a square into 100. But still the answer is not complete. So you need to wait for another 3 minutes for your pizza. See guys, we need to find out the relationship between a and r, right? So now you can say, no, it's a kind of face-centered cubic unit cell. So consider a, b, c again. By this time I think you will be expert in saying that under root 2a is equal to 4r. This you know, okay? So what will be the value of? So you can say, no, 2a square is equal to 16r square. So a square will be 8r square, right? So when you know the value of a square, now you can just put it in the formula. So the percentage efficiency will be 2 into pi into r square to be divided by a square, which is 8r square, multiplied by 100. R square got cancelled, so it is pi by 4 into 100, and the answer comes out to be 78.54%. With this particular answer, I can give you the permission to go and have at least 2 pizzas after this particular exercise. So option number D is the correct option for this particular question. Okay. So guys, this was all about how you are going to eat pizza while doing the chapter solid state, right? With this thing, I think I'm almost completed with doing the theory part of solid state. JEE Mains, JEE Advanced, CBSE NEET, everything is done. So you have this chapter all together in one go. Take sufficient time so that you people do not feel burdened. Try to do all the lectures one by one. Try to do more of the questions as well. Okay, so till that time, eat so many pizzas and enjoy the bestest to the best level, and then I'll be meeting you for my next lecture. Bye bye.